with HMC. There were some minor
site diagnostics, and they will tell us about machine learning in optical metrology.
Okay, thank you. And thank you for your invitation. It's I feel really fortunate to listen to all these interesting talks. So what I was thinking of doing is to describe how we use machine learning in optical metrology, which is basically what I've been doing, roughly speaking, for the last decade, and specifically show you how we do that for a use case, which is what I'm involved with right now, and that is blood diagnostics. So I'm currently working at a company called Site Diagnostics, which is a company that manufactures blood diagnostics tools, which is what you see here, using optical metrology and machine learning. So, so here's the agenda. I thought of firstly introducing the use case, then describe for you what is optical metrology, how we model signals with optical metrology, why I think it makes sense to use machine learning in that context. And then what I was trying to do here is to describe several challenges that we faced and try to make a connection with what you guys are what you guys would perhaps find useful. Okay, so let me start with the introduction. So, a fundamental test in blood diagnostics is what is called the complete blood count. It's what you do when your doctor, often what you get when your doctor sends you to a blood test. It's basically a measurement of the statistics of blood cells, essentially the concentrations, statistics of their sizes and their hemoglobin content, and it's basically the most common test that is being ordered, and it's important for various things. For example, differentiating between bacterial and viral infections, monitoring different types of patients, early detection of blood cancers, and other things as well. But in general, I think it's fair to say that it provides you with a general assessment of one's health. And the traditional way of doing such tests, which is what happens to the blood sample after it's being taken from you, it gets sent to a central laboratory, and a technology called flow cytometry is being used, whereby essentially the blood is being flown in these very narrow tubes, where each individual blood cell is measured, and essentially a laser light is shined on each of these blood cells, and one detects the fold scatter, side scatter, and other type of emissions, providing you with a handful of features per cell, and allowing you to, for example, classify the different type of cells that you may find in one's blood, like different type of monocytes, lymphocytes, and all these other type of cells that we have in our blood. And this is how these things look like. They are kind of somewhat bulky machines. They need to be operated by expert individuals, and they require lots of maintenance, because all these very small tubes require lots of cleaning and maintenance and so on and so forth. And this is where our product comes in. It's basically aimed to be a CBC analyzer for point of care, and something that can be used by small physician offices, for example. It provides you lab-grade accuracy, very simple to use, very little maintenance. And what enables all that, as I'll show you in the next slides, is the technology, which is optical metrology and machine learning and computer vision. Let me tell you what are these. What is optical metrology? And so basically, inside Olo, we have an optical microscope, which is able to measure the reflectance and transmission of both bright field and fluorescent signals. And for each blood sample, we can get thousands of high-resolution optical images at multiple wavelengths, multiple foci plane, and multiple sample positions. So this is how one's blood looks like in these images. You can see the red blood cells. These shiny objects are white blood cells, and they are shiny because they emit a certain fluorescent signal in our device. And then we take all these tons of data and model it in a way that it will provide us the CBC results with high accuracy. So here I've just jotted down an example of several of the measurements we measure, such as the density of white blood cells, red blood cells, the volume of a mean red blood cell, the amount of its hemoglobin, and so on and so forth. And you see that the level of accuracy and precision is required to be quite good. So these are essentially FDA requirements. And what I want to show you is how we get to such results. I wanted to just put things in a broader perspective. So optical metrology has been around for decades, well before the recent boom in the last decade in machine learning and deep learning. And one main example is what people call process control for semiconductor manufacturing. So this is the process in which we manufacture chips, computer chips. We basically print, if you like, these chips and perform a lot of other physical processes on what people call silicon wafers. Each such object contains hundreds of computer chips, and truly this is one of the most complicated physical processes that I think is around. In order to do that, there are huge fabrication plants, such as this one. TSMC is one of the only and main companies in the world that is able to do that in Taiwan. And because this process is so complicated, it has very tight tolerances on the accuracy of the transistors that is printed and manufactured. And so we measure them very frequently, typically or predominantly with optical measurements. So these transistors are being beamed with various wavelengths, polarizations, beam profiles, and so on, and we get signals which we then model and extract from these signals the geometric parameters of these things, which are very small, as you see. Now, traditionally, the way these signals were modeled was never with machine learning. It was with the traditional physical modeling. And the reason is that the underlying physics of this process is very well established. It's essentially light propagation through material. We have Maxwell equations. We understand them very well. We know how to solve them. And this is what has been used for decades. Also, the measuring tools are very accurate. They are very stable. They have very tight tolerances, typically at the sub 10% level. And so what people used to do is measure some object, get its signal, and then simulate in real time the solution to Maxwell equations of such an object, and fit the results to the measured signal to extract these geometrical quantities. And this has been quite successful. You can get accuracies at the level of sub-angstrom, actually, when people do that to important enough applications. Now, because this is a Lattice audience, I wanted to make contact with things around. So, the methods of solving Maxwell equations are essentially ab initio classical field theory. So either you discretize Maxwell equations in real space, however, not on a cubic lattice, it's not enough. So you do some finite element analysis, or, and this is predominantly the main method that people use in real time, it's called the rigorous coupled wave analysis, or RCWA, which is nothing but defining Maxwell equations in momentum space, putting a hard cutoff on the, on the hard UV cutoff, and solving them in finite form. And this is what essentially people use. There are other methods that you can think about them as effective field theories, like geometric optics, effective medium theory, and so on. But RCWA is the main one. So an obvious question is, why do we need machine learning? Here is everything is so great. So let me show you some example. This is a use case where one wants to measure the resistivity of nanoscale wires, such as those pictorially represented here. It's the spread thing. So again, you think you have this on your chip, you model it, you simulate the way Maxwell equations will tell you the light should be reflected, and you get back the geometrical parameters of this object, the height, and so on. And from them, you want to control the resistivity. So some results from one of the main chip manufacturers in the US are these. So what you see on the y-axis is the trench height. In the x-axis, you essentially see the resistivity of some electric test that you can perform and use as a ground truth. And you can see correlations are not amazing. Different colors are for different designs of chips. And importantly, if you look on this plot on the right, correlation is much worse. And we think the reason here is that there are lots of finite volume. So the volume on which this was measured was much larger than what the numerical simulation was able to simulate. However, if you just do machine learning, you get something much better. And, basically because all these numerical issues and other issues, such as the uncertainty you have on the original geometrical model you started from, do not exist when you do machine learning, and you get much better results. So much better correlations. And so in general, what we find in our industrial use cases is that there are lots of physical type of noises we simply do not know how to model, such as tool noises like optical aberrations of different types, environmental variances like temperature, which may change the index of refraction, for example, or other things. But sample variance, like for example, in the context of blood diagnostics, how will a certain person's blood oxygenation level change the model that we have in mind to use to predict the blood quantities thereafter. And this is exactly where we find machine learning is useful. So let me show you another example. And this now will bring me to the blood diagnostics use case. What you see here is a scanning electron microscope image of a red blood cell. Its dimensions are roughly 2 microns width and 8 microns diameter. And it's of clinical interest to know what is the volume of this object, because it, for example, tells you something about the ability of the cell to carry oxygen. And we can think about a physical model to calculate the volume. So we take a snapshot of such a cell in our device. It kind of looks like this. And we can grab the area of the cell from just simple image processing routines, and As far as the thickness, we will claim that the absorption of light is proportional to an exponent of minus the thickness, and we can get the thickness by taking the log. Importantly, there are bold assumptions being made here. For example, that the extinction coefficient of light is some known and stable parameter, that the cell is indeed aligned such that this is its area, and so on and so forth. And so these are assumptions we want to avoid. Despite that, we get with such a model quite decent results. So this is a correlation between the physical model results and the ground truth. But still, the correlation is not amazing, and on top of that, if we want to make it better, we need to also take care of, for example, environmental conditions. So just recently, there was a paper showing that the temperature can change the way red blood cells look like. This is optical holography results over red blood cell at different temperatures. So there's a lot of variances. We simply will not have any chance of modeling physically. While in the next slides, I'll show you how we model it with machine learning, and we get results like this. Much better. You can see that the scatter of points is smaller, and also the bias goes down. So my aim in the next slides is to show you how we do this. And there are challenges with machine learning, and I hope to to find some generalities, and perhaps this will be useful for you guys. The way I'm going to do this is discuss a particular problem, the classification of white blood cells. So this is again an image taken with our device. These shiny objects are white blood cells. And in a normal person's blood, there are 5 main different types of white blood cells. This is how they look like in our device. And this is how people have been used to seeing them for decades with ordinary microscopy. So the main ones are these 3: neutrophils, lymphocytes, monocytes. They are responsible for how we fight viral and bacterial infections. These are less common and mostly involved with allergies. Now, importantly, the first thing we do is use some subject matter expertise to help us classify them. So let's look at these lymphocytes versus these neutrophils. It's clear they look different. So lymphocytes are somewhat smaller. They have a single nucleus, they both have single nucleus, but they have a nucleus which has a single lobe, while neutrophils have between 2 and 5 lobes that you can see here. And the nucleus is filling almost the entire cell, while here it's not. So if we want to distinguish between them, we can easily or relatively easily define some set of features such as these ones. And the size, the number of lobes, the ratio between the nucleus and the cell size, and so on. And you can find many others which I will discuss. Plotting how these different cells, different white blood cells look like on a scatter plot of cell area feature and nucleus to cell size ratio, they look like this. While if we single out the neutrophils and lymphocytes, they look like this. So we can even try linear classification, and it will give us quite good results. So putting it all together, we can start with our images. We find the white blood cells. We featurize them according to some prior knowledge, which is biology and physics based. We tag them. We know a priori which one is a neutrophil, which one is a lymphocyte. We train a classifier, and that's it. we can then run a test time and say each one which is which, and report some statistics to the user. And unfortunately, this idea does not work. So let me show you why. Which is, by the way, this is obviously straightforward supervised learning. Why does this not work? So our images with Olo are kind of the first of their kind. We cannot really a priori say, this is a neutrophil and this is a neutrophil. We do know how to say that traditionally from decades of microscopy on the microscopic images that people have been using, but not with our device. And we do not have a one-to-one correspondence between a single cell here and a single cell here. It will be very difficult to do so, perhaps even impossible. There are completely different routines. And so what I'm essentially saying is that we do not have a per sample tag, which means we cannot use standard supervised learning. You cannot find such images online, unlike other situations. And people are, when I say people, I mean microscopists or specialists are not familiar with these Olo images. So we cannot do this exercise because we simply do not have a tag per image. So what can we do? What we do have as a ground truth is a statistical statement. We know that a certain person's blood has some statistical characteristics, such as that the amount of lymphocytes in their blood is 35%, or monocytes is 8%. And so what we're going to do is to use these counts. And to do that, we again start from the images. We detect these white blood cells. We still featureize each one. And now we will train an algorithm to tell us what are these statistical quantities. And pictorially speaking, it looks like this. We basically concatenate or stack all the white blood cells or some white blood cells that we find in a certain set of images. We stack them together. You can think about this as if they are different channels of the same object, of the same sample, and we plug them into a huge neural net, which will then spit out the statistical stuff, which is indeed associated with all this stack of patches or with a single sample of one's blood. The problem is here that we will have a lot of weights to calibrate, and so what we do indeed is use some simplification of weight sharing by essentially saying that these patches all should go through the same type of neural net. So we pass them through the same neural nets. So I won't be able to show you exactly the architecture, but to make things more clear, I did find some paper online which does something similar. So this is a paper from 2 months ago from Duke University of some researchers aiming to diagnose COVID with ordinary microscopy images. So they do again the same. They capture some of the white blood cells, which look like this. And while they don't have a per image ground truth, they stack them together and plug them into a deep learning system, which outputs the COVID diagnosis. So specifically, you see the pictorial architecture here. All these images go through some feature extractor, which extract features for each one. Then they have another step where these features go through a model which is trained to provide them with the weight per image. So this is the cell importance here. It's essentially an attention mechanism which tells you how much each image will be important for the overall patient prediction. And then this, together with these features, go through a model that predicts whether a person has COVID or not. So I'm not familiar with the other papers in this context, and they have results like this. So this is the ROC curve, roughly speaking, 80% sensitivity and 80% specificity. Which is good enough, I think, for first attempt. Okay, so going back to what we do, so here are results from the type of analysis I showed you. This is from a certain, this is just a snapshot of results. We have much more from a major hospital here in Israel. So you see the correlation between the prediction of the model and the ground truth for 4 of these white blood cell concentrations, and they look pretty good. This is a more comprehensive data set from our clinical trials in 2019, for which we were approved by the FDA. So you see here in blue, you see the specs that we guarantee and were requested to be better than, and in red you see the performance, which is clearly better. So this is the performance. One may ask, what happens if you do not know which features to use? For example, in the context of white blood cells, there are different types of lymphocytes, normal lymphocytes and lymphocytes that are present in samples whose, that belong to patients that may have cancer or that may have other type of diseases like viral diseases. And they look differently, so we would need to find features that capture both of them and separate both of them from the other type of cells. Other examples for that make it difficult to capture features are biological variances or tool variances. For example, the tool may be out of focus, and we still want this object to be classified as a neutrophil. I won't speak about staining at the minute for the moment. And in the context of red blood cell properties such as the volume, which is what I started from the beginning of the talk, it's not really clear which features should I use for red blood cell. I mean, I can think about the area and maybe some moments of its intensity, but it's not really clear. And to solve this problem, we do a simple thing, and that is to let the computer learn the features by deep learning. So everything follows through. We still have this statistical ground truth, which is the major point here, but the features themselves are not designed by a subject matter expert, but rather learned by the training procedure. And this shows you some results from that. You see the mean cell volume, the amount of hemoglobin, everything is within spec. This is the density of platelets versus, again, everything here is versus the ground truth. Okay, so if I recap this part of the talk, what I wanted to bring through is that the way we solved the absence of labeled data, or the fact that it would have been very costly to label each individual image, is by using as ground truth numbers that represent the statistics of a group of samples, and added some weight sharing to state that the members of the groups should all have the same weight, same featureization, for example. The second thing I wanted to emphasize is the fact that we combine featurization by subject matter experts and machine learning. So it's obvious that this makes sense to do from this plot here, where you can see with your eyes that only two features can separate these two blood cells. We have many more features, so you can imagine we get better results. But I think this is a major point that we use. And the last thing I wanted to show you is how you can go even further and combine machine learning and physics together to make to solve the data problem or the absence of labeled data or the cost of data even further. So here I will jump back to the semiconductor use case because there we actually, solve Maxwell equations. So the question is, can we use this wisdom on how we solve Maxwell equations and have been doing that for decades to make things easier for machine learning? So again, we have the structure we are after. We measure its signal. We solve Maxwell equations and fit that to get these parameters. And so what, together with some smart people at Nova, what we did is the following. We realized that we can use Maxwell equations or the Maxwell equation simulator to model a rough optical signal for the measured sample. And then essentially use this signal to concatenate it with the ordinary signal, the measured signal, as a feature. So in that sense, we are doing some of the featurization for the network with some clever, crazy algorithm called Maxwell equations. And so let me show you some results. It's all in this IP here. So here you see the accuracy that you obtain with this method. Different bars stand for different combinations of features. And this one here is the result you get when using only the measured features. While you see that once you add the Maxwell equation generated features, you can actually do much better, almost 50% better. What you see here on the left is the accuracy as a function of train size in some units. Doesn't matter which units these are, but these units essentially count the amount of data you needed to train the model. And the y-axis is the accuracy. So this black curve shows you the benchmark, which is essentially some machine learning model that does not know about this trick. And in gray, you see the results of combining the model with some physics-aware featurization. And the point is that you get better accuracy, and you're also converging to this accuracy faster. So if you only have, suppose you want the accuracy of around 7 nanometer here, you can get it with 20, at this amount of data over here, while with the ordinary machine learning, you would need, a large factor from that. So that's essentially the value. Okay, so the last thing I wanted to show you is how we deal with device-to-device variability. So that's a possibly major issue in use cases where you have multiple devices all need to provide the same results in the same sample. But we know each device we manufacture is slightly different. It's a optical microscope. So each optical microscope we will manufacture will have slightly different optical aberrations. It will have different light source spectra, alignments will work slightly differently, and so on and so forth. But we do want all devices to behave the same. So this is the challenge. As an example, what you see here is data from some analysis we did. On the y-axis, you see the bias or the inaccuracy in specifically in monocytes, which I remind you are one of these 5 major blood cells, white blood cells we have in our blood. And on the x-axis, you see one of the optical operations that people typically talk about when they characterize an optical microscope. So astigmatism is an optical aberration that causes a point light source to smear kind of in the 45 degrees axis like this, typically formed by twists of various optical devices like mirrors in the microscope. And you see some correlation between each point here is a device. And you see some correlation between how good the device is in the sense that it has low or medium astigmatism and how bad the inaccuracy of monocytes is. And especially we want to avoid this stuff here. We will never be able, so obviously you want to manufacture devices that have low astigmatism, but some of them will have the largest astigmatism, and you don't want them to be completely off in terms of performance. So one of the solutions we had is to essentially add something you may call a device signature or some meta features to the features that we use in our original model. So originally we just said, if you like, all devices are the same. All you need is to capture features from the person's sample, and you will get train the model. But now, if we know some devices are different, we can add them as an input feature. And essentially, if we now train this network that has more features, we kind of calibrate a bit the weights of the original model in a per device way. And in some sense, you can think about this. And the point being is that this is costly, however, because you kind of need to measure this signature per device. So some results, looking at these red devices that have a largish monobias. This is how these guys look like when we plot them. This is the original result for the original model. We have, on average, all these devices have a bias of 1%, while if we add these extra features, we essentially half the bias and get half the inaccuracy. You can also see that from the plot. You're very, very careful. Okay, so this is one method we used. The second method is essentially say, well, okay, but now we've been manufacturing lots of devices, not tens, but in the hundreds and thousands. We do not want per device to kind of measure its signature. I didn't mention how we do that. Some of this measurement is complicated, and it will be great to avoid it in the manufacturing process. But now, if we already have all these devices, we can simply try to fit all of them together and train all of them together with a single neural net, which will perhaps choose features on its own that are, for example, insensitive to astigmatism. So to be able to do that, you need your train set to be varied enough to have high astigmatism devices, low astigmatism devices, and try to train the network. And indeed, this is what we did. So these are the results. So this is the original ones that I showed you a minute ago. Well, if we forget about these per device signature meta features, we just have a CNN, and we get an even better bias. This is how it looks like over here, and we are within spec also for this algorithm, but we are much better with this one. Okay, so basically, let me just recap and say a few words about things I did not discuss. So I think my point here was that for the industry and healthcare use cases, well, even though you're using optical tools that are well known to be very well modeled with ab initio physical equations, even there we know that to get good enough accuracy, we won't be able to get there without machine learning. However, in these use cases, it is always the problem of getting data. Data is very expensive. The ground truth is usually generated by devices that are expensive to operate, complicated to operate, and so on. That's the basic reason you are doing it differently. And so it's very expensive. However, what I showed you is that I showed you two methods of solving it, either by using some statistical statements on the samples or combining machine learning and feature engineering. And there are other things that you can do, which I didn't describe. Things I can mention right now. So in order to get, usually when we do a regression, for example, we have some MSE loss function, which tells us that we want to minimize accuracy of the prediction versus the ground truth. But sometimes, firstly, sometimes this is not entirely what is needed. Sometimes you need to optimize accuracy and, for example, precision, or balance statistical errors with systematic errors. And one way to do that is to use multitask loss functions that have both ingredients in them. And while doing that, you also figure out that actually you need less data because you have more constraints on your weights through the loss function. Something else that people use in the industry is, as we just heard, to speed up simulations. Some simulations in specifically optical metrology can take weeks or months, and there's a lot of activity in optimizing the numerical code and so on, but you can get very far with replacing these simulations or ingredients of these simulations with machine learning that is trained on a subset of the data, and there's a lot of activity there. Some physical processes we do not know how to model. For example, I've spoken about optical physical processes, but in semiconductor manufacturing, for example, there are lots of chemistry involved processes, which people simply do not know how to model well. And having measurements for these processes allows you to model it with data science, and that is useful for making predictions and so on. And finally, one thing that I want to mention is transfer learning. So you can think about, just a second, you can think about training a network with simulated data, which will essentially be a way of inverting Maxwell equations, because you start with signal and end up with underlying parameters. And once this network is trained, you can now use, with the simulated data that you have abundant and it's rather comparably cheap, Then you can do a transfer learning and fine tune the network with real data. And this is has also been found to be useful. And this is what I meant by this. So I'll just end by thanking you and thanking my collaborators at site that put together some of the slides here. And if you are interested in more data and info about the blood diagnostic use case, you can find it here. And maybe I should add another one for the semiconductor use case later. So thank you very much.
So let's thank Barak for the nice talk. So are there questions? So I will start with a question myself then. What do you see as the main challenges from the machine learning point of view? I mean, I see that now you have used sort of out-of-the-shelf models. I mean, do you see limitations in these models? And if there are limitations, where they actually are more obvious?
I think every use case is special. So, for example, when I mentioned this multitask loss functions, sorry, most of the literature you would find and most of the ready-made models you would find only optimize accuracy. While some use cases would say, no, I only want accuracy to be as good as this level. I don't care about optimizing it further, but I want that each device or each tool that measures the same sample will have the same result down to a very, very tight spec. So you can think about how to solve that, but if you do, eventually you realize that you need to complement your loss function with some term. And it is not often the case that these terms are easy to differentiate with normal methods. So you need to kind of come up with various tricks to perform the automatic differentiation and so on. So what I found, the usual thing people will say is that the main challenge is data, and that's true. But I think what I found is that whenever you go to a real use case that not only cares about ordinary regression performance, you end up with optimizing some multitask loss function that you will not find in the literature. Yeah.
Okay, no, thank you. So it's multi-object objective objects optimization then. Yeah, I don't know. Is there? Yeah, I can see a question by Sebastian here.
Thanks, Barak. So I was just wondering, since neural networks are very robust to against massive label noise, what would happen if you, in your blood cell classification, use this ensemble label for single cells and just accept that most of your labels are just random, but by the imbalance of the probability distributions that give you the is he still there?
Yeah, I'm here.
Okay. So we had a technical problem. So if you just train your neural network in the most simplest way to classify your blood cells and accept that you have this massive label noise, but you still have a tilt in the right direction with your training signal, what would happen then?
Well, obviously the straight answer is that I don't know, but I think the real challenge here is that I think one of the reasons we did what we did and did not want to make this assumption is that it would be very hard to get oneself convinced that regulatory-wise, that you have some trust in your ground truth, right? I mean, you eventually want these predictions to lead the physicians to make decisions. So if I write down an algorithm whose ground truth is some rough statement stating that, yes, this looks like a neutral field, it would be very hard for me to convince with data that I did the right thing. While the ground truth that we had is statistical in nature. And so that makes more sense. But yeah, I think this is an interesting point to examine. I don't think we ever examined how robust our neural networks in this context to label noise. But yeah, that maybe one can do that. I'm just thinking about what would be the use case here for us. But yeah, maybe worth thinking about.
Okay, thanks.
Yeah. Any more question from the Zoom audience, for instance? From the Trento audience? So, me too. Now, let me ask then one question myself. You say that computationally, your methods are very expensive. This is just a curiosity. Which type of resources do you use for the computation?
AWS. You mean the computation?
Yeah, computational hardware, software library. What do you use?
Well, I mean, let's try to be more specific. So the computational resources people use to solve the physical equations are just you know, high performance computing, which will not be on the cloud because these things are considered you know, the physical models that people have in mind when they design chips are considered you know, IP. But the machine learning models that we develop, we simply use AWS resources, which is very kind of easy to use these days, and very efficient, right? Because you can decide as per your use case how many resources you need, and you don't need to commit yourself to buying your resources your own and so on and so forth. So I think it's been, and also the computational environments there are very easy to set up and typically contain everything you need. So saves you a lot of hassle.
Okay, so thank you very much. One last chance to ask a question. So if there are no further questions, then let's thank Barak again.
Thank you.
And we give you, I mean, we will see you all this afternoon.